So we can have a couple situations here. Now, insoluble, meaning not soluble, insoluble ionic or molecular compounds. So that means they can't dissolve. They don't break apart easily, and water doesn't give enough attraction to pull them apart. They do not dissolve to any great extent. So we use this solubility table for ionic compounds to see if it does dissolve well or not. Okay, so we are going to become really familiar with our solubility table when we're doing this chapter. So example, silver chloride. So take out your solubility table. It's probably like you can use one in your data booklet, or there's a really tiny one on the back of your one data sheet, if you'd prefer. So in your data booklet, it's page 6. Okay? So when we find chlorine ion, and then we go down to silver, so silver chloride, it's slightly soluble, it says there, which means like it's hardly soluble, that it's pretty much insoluble. So we could take silver chloride, but it's not going to dissolve in water, and so we can't write aqueous with silver chloride. Okay, so it's like silver chloride, solid. If I dissolved it in water, it would just be silver chloride, solid. There's nothing changed. So this is the dissociation equation for silver, just representing that if I put it in water, nothing would happen. Also, like sugar, or sucrose, so some sort of hydrocarbon. Well, sugar dissolves in water, but okay. It must be a different hydrocarbon. Like, it's probably like some sort of oil kind of thing. Yeah. Oily. Okay. The next one. Soluble ionic compounds. Dissolve to a great extent to form ions in solution, which is most of like the point of this chapter as we have discussed. Ionic bonds are broken, right? That's the first step, is breaking the bonds of the solute. Okay, so you use your solubility table. Now, think about a base as an ionic compound. So when you see like, how do I know if it's a base? What in the compound tells me it's a base? Oh wait, yes. We're actually going to learn that some bases include other things, right? Because remember, like an exception is like ammonia, which is NH3. That has no OH in it, but it's a base. So I'll teach you why in a little while, but anyways, whenever you see bases, they include ionic compounds that are soluble. They turn litmus paper blue, as we've seen and discussed lots. So when we do this, you balance the number of ions when you're writing out your formula. So say you have NaCl solid. If I have an arrow and I'm just representing that I'm dissolving it in water, what I have left over is sodium ion, aqueous, and chlorine ions, aqueous. Okay? Write down that. Okay. And remember on your data booklet where it says group 1 ions, don't forget about those, right? Remember group 1 is everything here. So all of these things, if you combine them in this, they're soluble. So just don't forget about that. Okay, another one. Say we have potassium hydroxide. Remember that, as you said, that OH is a base. So it would dissociate into these ions. I'm just, you'll be on the video. Oh, Okay, so that's, okay, so but if I had, like, say, oh, what can I give you? Like, say I had MgCl2, okay, solid. Well, that's going to dissociate into Mg2 plus aqueous plus Cl minus aqueous. But it's not balanced. So all you do is you put a 2 in front of the Cl. Okay? So that's what it means by balance the number of ions. If like it's different than from the front and the back, the front from the back. Reactants and products. Use real words. So, the third one is soluble molecular compounds. They dissolve to form molecules in solution. So, how does that happen? Well, intermolecular forces, because we know intermolecular forces are in our molecules, so our London dispersion, dipole, dipole, and hydrogen bonding, those need to break first. And then they're able to dissolve. So, this is like a sugar. Now, it does not dissociate. You see there? It doesn't break down into smaller bits, right? It doesn't break down into bits. But we can write it as aqueous, because we know it dissolves. Okay? See the difference between the molecular and the ionic compound? Yeah. So this is like sugar. You know that you can dissolve sugar into your tea or whatever. But it doesn't break down into ions. Because there aren't ions. So what bonds stay present? If the intermolecular bonds broke, what stays present? Intra. Yeah. The intramolecular bonds, remember, covalent is so much stronger than ionic that it won't break, right? Ionic was low comparatively to covalent. Molecular compounds do not have a solubility chart, but there's a few patterns that can help us figure it out. Oh yeah. Okay, so flip over your page there. Non-polar molecules generally don't dissolve in water. So this is where we can use our bonding unit and kind of apply it to this next step. Polar molecules may be slightly soluble in water. Because they're able to be attracted to the water. And then polar compounds with hydrogen bonding, they're going to really dissolve, right? Because they'll be, since the water has hydrogen bonding too, they'll create new bonds, new intermolecular bonds. So, what I think we'll do is we'll leave it there for today. We'll finish that page and do number 4 later. So, what I want for homework is that